Welcome to an introduction to logarithms. Today we're going to talk about logarithms and a couple of their properties. And if you've never seen a log before, I think you've tuned into the right video. So, you've been given problems in the past, no doubt, that ask you to find the value of a power. So let's just pick a number here, like 2 to the 4th. They'll say 2 to the 4th equals what? So you multiply by a bunch of 2's and you come up with 16. So what was missing was the value of the power. A logarithm is a related question, except they'll ask you something like this. What's the base 2 log of 16? Now, according to this definition, the base 2 log of 16, the base b log of x, is equal to a number y if and only if that base 2 raised to the y power makes the number inside the log, the x. So in other words, if you wanted to go about it this way, you could answer this logarithm question by answering this power question instead. 2 raised to what power equals 16? Now, of course, it helps to know some powers to get around with these. But you can do this with pretty much any base. You wouldn't just make sure it's a positive base. And it turns out 1 doesn't work very well for a base at all. Here's another logarithm problem. What is the base 3 log of 729? All right, not everybody knows this one. But if you understand the concept, what's being asked here is, I would like to take the base 3 and raise it to some y power and end up on 729. Okay, so you can quite literally just take your calculator and start taking powers of 3. 3 to the 3rd is 27. 3 to the 4th is 81. You're not big enough yet. 3 to the 5th is 243. 3 raised to the 6th power. Put a 6 right here, you'll get your 729. So you can see how I was looking for the correct exponent, and that's what logarithms are. They're just exponents. I give you a base. I don't tell you an exponent. I'll give you the result of the power, the value of the power. You have to go find the exponent. So that's what logs are. Okay, a couple things to keep in mind. If you're taking a log such as, let's go back to base 2 because that's pretty easy to work with. If you're taking a log of some number and the answer, the argument inside the log is smaller than that base, you probably need a negative exponent. It turns out the base 2 log of 0.25 is negative 2. Why? Well, here's how you can check your work. Take the base 2, raise it to what the logarithm is, or what you think it is, and remember that a negative exponent is equivalent to 1 over that same positive exponent. Same power, but with a positive exponent in the divisor. And that's 1/4, and that's 0.25. So, yeah, that's the correct logarithm. Here's another one that will come up. Somebody will ask, find the base 5 log of 1. Okay, you'll learn to like a problem like this because it turns out the answers, regardless of the base, the answers turn out to be 0. Now, how can you know that? Well, just restate the problem like this. Say, I don't know what the logarithm is, which means I don't know what the exponent is. I know what the base is, okay? And I know that the answer, when raised to this logarithm or this exponent, is going to make 1. Well, you probably know 5 to the 0 power makes 1. So the base 5 log of 1 equals 0. Now, our number system is based on tens. And for that reason, a very important logarithm is a logarithm with a base 10. There are things like pH of pond water or soil that are based on logarithms of base 10. Also earthquakes. And I assume it's just because our number system is based on 10. So here's a base 10 logarithm problem. It's a common logarithm problem. And you won't see it written like this very often. If I ask, what's the log base 10 of 1,000? The answer is 3. And you can check your work by going like this. 10 to the third is equal to 10 times 10 is 100 times 10 is 1,000. So you got the correct exponent. You found the logarithm. There's a catch. This problem is rarely going to be written like this. Again, this is 10 is such a common base for a logarithm that more likely than not, you'll see the problem written like this. Find the log of 1,000. Okay, you must assume that by default the base is 10 here. So I've written this question and I've answered it twice now because it's the same question. Okay, here's another common log question. What's the log of 10,000? Well, that's just a higher power of 10. Turns out to be 4 because 10 raised to the 4th power is just going to add another 0 on here and give you 10,000. One more common log problem. Common log. What's the log of 0.01? Well, notice how they didn't show you the base, but you know what it is. It's a 10. That's the default base for the common log. And the argument inside the log is smaller than 10. You're going to need a negative logarithm or a negative exponent to make this happen. So it turns out to be -2. Now, how come it's -2? Because 10 to the -2 power is 1 over 10 to the +2 power, which is 1 over 100, which is 0.01, that number. So the common log of 0.01, whether I show you that base or not, is -2. Another important log is called the natural log. Now apparently these are the only two logs to be important enough to earn a position on this calculator's keypad. See where it says log right there? Yeah, that's the common log. That's base 10. And by the way, if you hit the inverse function up here, behind the common log is the base 10 exponential. We'll talk about inverse functions in just a minute. Now there's another button here that says ln. That stands for natural log. And behind it, you'll see, I think you can see it says e to the x. So natural log is a log that's based on e. There are two ways to write it, of course. You can write base e log, or you can write ln. Which one are you more likely to encounter? 99.5% of the time, you're going to see it written like this. Okay, and in case you've never seen the number e before, or you missed the previous video, the number e is an irrational number that looks like this. At least that's the ones digit and then 9 decimal places of e. It is like pi. It doesn't really stop there. It's infinitesimally accurate and can't be written down as a decimal. It's an incredibly important number in mathematics, especially for modeling exponential growth and decay. And so it's a base that gets used a lot, both in exponentials and in logarithms. Base e. Don't forget, e is approximately 2.72. Okay, so what are some natural log problems that we can do? Well, if they ask you to find ln of 5, you may be a little disappointed in that there's not a great way to do this without a calculator. You pretty much have to go to your calculator, hit the natural log button, and dial up a 5. And when the answer returns, it doesn't look so great. Well, but that's what it is. If you want nice, clean answers, so this is approximately equal to 1.609. If you want nice, clean answers, then all your arguments inside the natural log have to have something to do with e. So here's one, for example. What's the natural log of e to the 4th power? Well, it turns out it's 4. Because why? Because 4 is the number that you can put on the base of the natural log to get e to the 4th. It looks a little like circular reasoning. Okay, here's a more interesting problem. What's the natural log of the square root of e? Okay, so remember, there's another way to ask this question. I could say, what's the base e log of the square root of e? And the answer turns out to be 1/2. Because e raised to the 1/2 power makes the thing inside of the log, which was square root e. One more that you really ought to know is you ought to know that the natural log of e is just 1. Because e to the first is e. And you need to know natural log of 1 is 0. Because e to the 0 power makes 1. So memorize some of those fun facts. They will help you out. Now we want to take a look at inverses. So to do this, let's just pick a base. And let's pick an x value. And let's talk about what this statement is saying here. It's saying if you start with x equals 3 and use the 3 as an exponent on the power of 5, followed by a base 5 logarithm, in the end, nothing will happen. And I'd like to illustrate that now. So what do we say? Start with 3. And the first thing we're supposed to do is use the 3 as an exponent above the base 5. So we're talking about 5 to the 3rd power. That lands us on 125. Right, because exponentiation tends to make numbers grow. Not always, but most of the time. Now we're supposed to follow by this. So take the result and take the base 5 log of it. And remember, when you take a base 5 log of 125, you're trying to answer the question of 5 raised to what power makes 125? Well, guess what? It's 3. So you started with 3. The exponentiation made the value grow to 125. Okay, but the base 5 log of 125 took you back to 3. Are we going around in circles? Yes, we are. And that's kind of the point. You want to have inverse operations in mathematics so you can solve certain equations. And we'll get to those probably in a subsequent video. But putting all this together and comparing it to this is what I've done in this problem. I started with 3. I use it as a power or an exponent above 5. And then I took a base 5 log of that answer, and I got 3. So apparently a base 5 log and a base 5 exponential are inverses. And that's absolutely true. Okay, the other statement over here says that the base b log of a number used as an exponent above the b gives you that number back. So let's give you a quick example of that. Let's take the base 2 log of 32 and use that as an exponent sitting above a 2. Well, you got to start with the inside. So what's the base 2 log of 32? The base 2 log of 32 is 5 because 2 to the 5th power makes 32. So this part of the problem is just the 5. So if I substitute, I get that. And then if I take 2 to the 5th power, I get 32, which is exactly where I started. So, indeed, base b logs, base b exponentials are inverses. Okay, we're about 14 minutes into this. We're going to do as many log problems as we can quickly for the benefit of some of my students who are going to do an assignment with many of these same questions in it. So, which is different? The question, what power of 4 gives you 16? Why, that's 4 to the 2nd power. But notice that they're looking for an exponent here. So this is a logarithm question. And by the way, the answer to this is 2. This is not a logarithm question. This is a evaluate the power question, and you get 16. So apparently these were different questions. What is the base 4 logarithm of 16? In other words, 4 raised to the what power gives you 16? It's 2 again. And that's the same question as that. Here's the way you write it more symbolically. What's the base 4 log of 16? 4 raised to the what power makes 16? 2 again. So as you can see, these three questions are the same, and this one was different. Rewrite base 3 log of 9 equals 2 in exponential form. Here's the base. Here's the exponent that you would put on it. And the thing inside the log called the argument is the value of that power. Take the base, raise it to the answer to the log, get the number inside the log, the argument. So this is designed to get you thinking forward and backwards with logs and exponentials. Base 1/2 log of 16. So take a half and raise it to a -4 power, because that's what logarithms are. They're exponents. And you get 16 for an answer. You might want to convince yourself that's true. Okay, now we're doing the inverse of that. They give you a power problem. They want you to write it out as a logarithm question. Well, if this were a logarithm question, one of these three numbers would be missing. Yeah, it would be missing. Which one? That 2 would be missing. So essentially, they'd say, okay, I'll tell you the base, it's 6, and I'll tell you the answer to the power. The value of the power is 36. You tell me the exponent. Yeah, that's the log, and it's 2. Another example of that. Here's a base. Let's put it down here in the log. Okay? You're supposed to not know that this is 0, because if it's a logarithm problem, the logarithm is supposed to be missing, or the exponent is supposed to be missing. What you know is the answer to the power. And you're supposed to figure out what number is up here. So you just have to pretend this is missing, but of course it's 0. So that's how you would write this power in logarithmic form. And after a while, it gets pretty mechanical, doesn't it? Base 16 will make an exponent of -1 if you take the base 16 log of 1/16. Okay? What's the base 5 log of 1/125? Y is -2. Okay, now we get to evaluate. If I come to one I can't do in my head, I'll pull out a calculator. But this is the base 3 log of 81. So remember what's being asked. 3 raised to the what power makes 81. 3 to the first is 3. 3 to the second. 3 times 3 is 9. 3 to the third. 3 times 3 times 3 is 27. 3 to the fourth turns out to be 81. So the base 3 log of 81 is 4. You're aware that 7 squared equals 49, right? Okay, then you can do this problem without my help. The base 7 log of 49 is 2. You found the exponent. You found the logarithm. All right, just a few more here. Find a base 1/2 log of 1. Yeah, it might be easier for you to think of it this way. 1/2 raised to what power makes 1? Well, typically when you get 1 as an answer to a power, you must have been taking the what? It's the 0 power, and that's the answer to this log. Okay, find a base 5 log of something that's many, many times smaller than 5. You'll need a negative exponent. It turns out that if you calculate 1 over 5 times 5 times 5 times 5, you'll get 1 over 625. Well, how many 5s are here? 4 of them. So that's the same as 1 over 5 to the 4th power, which is the same as 5 to the -4th power. You found the correct exponent for the base 5. It's -4. And just a couple more here. We're approaching the 20-minute mark, so I don't want to do all of these. We did a problem similar to this in the notes. Base 10 log, common log. They were nice to show you that that's a 10. They didn't have to. If you didn't see a 10 here, you would assume that it's a base 10 log. But for 0.001, that's many, many times smaller than 10. The answer to this is going to be -3. And the reason for that? 10 to the -3 power is 1 over 10 to the 3rd power, which is 1 over 1,000, which is 0.001. Now, the good news about this problem is, if I put it on your quiz, you have a button on your calculator that will help you get it right. Of course you do. It's the common log. It's right here. It's next to the 7. So you go log 0.001. And sure enough, -3 is the answer. You can do this one on your calculator too. In fact, that's the best way to do it. Just use the button that says ln. So ln 12 does not turn out to look so nice. It's 2.485 to the nearest thousandths. And these last 4 are just to remind you about the inverse properties, for example, of a base 7 log and a base 7 exponential. You're just going to get your x back. This is a base 3 log, and this is a base 3 exponential. Applied to 5x, you're just going to get your 5x back. Now, remember, natural log has a base of e, so they could have written this problem as, what's e raised to the base e log of 4? I might do that one on my calculator, but it's just going to get me the 4 back due to inverses. And this is sort of the same thing in reverse. This is asking you, what's the base e log of e to the 4th, which of course is 4. And that concludes our introduction to logarithms. My name's Eric. I hope you learned something. Have a nice day.